She is a senior scientist and research manager for the Infosec research group at SINTEF, the largest independent research organization in Scandinavia. She has a PhD in information security. She is also an associate professor at the Norwegian University of Science and Technology, where she teaches a class on incident response and contingency planning. She has experience as a team leader at the Norwegian Cybersecurity Center NorCert, where she did incident response handling for cyber attacks against Norway's critical infrastructure. She has R&D experience with connected cars, technology, and she has participated in standardization work on intelligent transport systems at ETSI. She is currently, and if that wasn't enough, she's currently doing research at the security of her own personal critical infrastructure. She has an implantable pacemaker that's generating every single beat of her heart. She loves to break crypto protocols, but gets angry when broken crypto is in her own body. Can we give a round of applause for Dr. Mo?
Thanks for the introduction. I'm really happy that I was invited to be here. Can you hear me okay through this mic? Or should I bring it closer? It's okay? Yeah, okay. So let's see if the technology works. So I'm a security researcher, and I'm a patient. Every single beat of my heart is generated by a medical device, a pacemaker implanted in my body. 5 years ago, I woke up lying on the floor. It turned out that I had fallen because my heart had taken a pause, long enough to cause unconsciousness. So to keep my heart beating and prevent it from taking pauses, I needed to get the pacemaker implant. This little device monitors each heartbeat and sends a small electrical signal directly to my heart via an electrode to keep it beating. But how can I trust my heart when it's running on proprietary code and there's no transparency? When I got the pacemaker, it was an emergency procedure, so it's really no option to not have the implant. I needed it to stay alive. It was, however, time to ask questions. To the surprise of my doctors, I began asking about the potential security vulnerabilities in the software running on the pacemaker and the possibilities of hacking this life-critical device. The answers were unsatisfying. My healthcare providers couldn't answer my technical questions about computer security, and many of them hadn't even thought about the fact that this machine inside of me is running code inside of my body. This is why I decided to seek out this information myself. Imagine that this is your heartbeat. A heartbeat being controlled by a machine that is running code inside of your body. Wouldn't you also like to know if it can be trusted? So I'm here today to talk about my security concerns about the pacemaker. And I know there's a lot of clinicians inside this room. That's unusual for the type of conferences I speak at. But I'm really happy that we have clinicians here today. But anyway, I'm going to give a small biology introduction to how the electrical system of the heart works. I'm sure that many of you already know this. So the pulse of the heart is generated by the sinus node. It creates a small electrical signal that makes the upper chamber of the heart contract for pumping blood. And then this signal travels through the heart's electrical system down to the ventricles. And when it arrives in the ventricles, you get the second contraction so that you get the maximum best pumping effect. Kadung. And there's a small delay in the signal. It travels through something called the atrioventricular node, or AV node, and that AV node creates that small delay that makes the pumping effect optimal for your heart. In my case, I got something called a third-degree AV block, similar to the patient that we saw in the simulation room yesterday, for those of you who were there. So the electrical signal just stopped in the AV node. It didn't reach the ventricles, and this happened suddenly, out of the blue. I didn't know that I had a problem with my heart until the day I suddenly just passed out. Hit my head on the floor, and I realized I had to go to the ER. I didn't suspect that it was something wrong with my heart. It was just that I had really hit my head, and I couldn't remember that I was feeling dizzy. It was just, suddenly, it was black, and I found myself lying on the floor. I had held a glass of orange juice in my hand because I was getting ready to go to work. I was working at the Norwegian Computer Emergency Response Team at the time, NorCERT. I was dealing with handling cyber attacks against Norwegian infrastructure. Getting ready to go to work, drinking a glass of orange juice. I was in a rush, I was standing up, and then suddenly I found myself on the floor, my head hurt. The glass of orange juice had shattered into pieces. I was laying in a pool of orange juice. I touched my head. I could feel it was sticky. I was concerned I was bleeding, but it wasn't blood, it was the orange juice. And I was a little bit dizzy, and I couldn't understand what was happening. And it turned out it was actually this blocking of the electrical signal in my heart. So I was admitted to a hospital, and I was put on monitoring for a week. And they recorded another pause lasting around 7 seconds. And I think 10 seconds is about the time that you will stay conscious without getting oxygen to your blood. So that felt a bit urgent to get the pacemaker. And of course, when they suggested that I needed it, I said yes. Of course, I want to stay alive. I don't want to have a heartbeat around 30, 40 beats per minute, because that's not really a good life to lead. And also, I was in a high risk of getting a sudden cardiac death when I had this condition. But it was fixed by having the pacemaker surgery. A very easy procedure. It took about half an hour under local anesthetics. So they just open up an incision about 5 centimeters in the chest. They make a pocket for the device. They put in the device, and I have 2 wires. One wire was screwed through. It was placed through a vein and screwed into the heart chamber. One in the upper atrium and one in the lower ventricle. So the upper lead is usually just listening to sense my heartbeat, because my sinus node is working as it should. So it just listens to the electrical signal that is generated by the sinus node. And then the second lead is listening in the ventricle to see if the signal comes through. And in case it doesn't come through, it will create a pulse by generating a small signal. And this is happening 100% of the time for me, because I'm 100% pacemaker dependent. Luckily, the heart has a biological backup system. So that too was actually saving me from cardiac arrest when my blocking of the electrical signal happened. So there are some cells in the ventricle that can take over the function of becoming pacemaker cells and create a small pulse that will keep the ventricle contracting. But the problem is that this pulse will become irregular, rhythmic. It's not connected to the nerve system of the body in the same way as the sinus node, so it doesn't know that if you try to run or exercise, you need a higher pulse. And also it can become very arrhythmic and make the heart stop. So that's the biology part of this talk. Here you can see a printout from my latest checkup, and you can see some of the hardware inside of my body that is keeping me alive. So I have chips inside of me that is controlling my heart. So from the printout, you can see a straight line at 100%, and that's how often my ventricle is paced. So that's 100% of the time. So every single heartbeat is actually because of the pacemaker. The lower graph, this is during a course of 24 hours. You can see that also the atrium is paced sometimes. And this is typically when I'm sleeping. And the reason for this is a configuration inside of the pacemaker, which is set at 50 beats per minute. And as a relatively young person, it's not uncommon that your pulse will naturally drop below 50 beats per minute when you're sleeping. So actually, it's unnecessary pacing because of that configuration. I tried to get my doctor to lower it to 40, but somehow he didn't want to do that. So still I'm paced in the atrium while I'm sleeping. So the opened pacemaker is actually a picture taken from the lab at SINTEF, where I'm doing some research on hacking and reverse engineering pacemakers and the devices that communicate with my pacemaker. And I was inspired to start this work 1.5 years ago. So it's 5 years ago since I had, or 5.5 years ago since I had the pacemaker implant. I was working at the CERT, and then I changed jobs 2 years ago. I started at the research institute. I was at a conference, and I was discussing with someone in the bar about my implant and how I didn't trust the technology inside of me, and how it felt to be a security researcher, not knowing how the security is actually implemented in your own critical infrastructure. And he was really fascinated about this, and turned out he organized a conference, and he wanted me as a keynote speaker for his hacker conference in Luxembourg, HackLU. So Alexandre Delano, he and my friend Aaron Leverett, who was also there, they sort of convinced me that I should stand up and I should use my story and deliver a keynote talk about this. And that sort of kicked off this project also, because when I was preparing to do that talk, I thought, what should be my main message to a room full of white hat hackers? I had done some research already, so I knew that little research had been done in the area of medical device security. There were not a lot of published results. So my main message was that we need more security research. We need more security researchers being inspired to look into the security of medical devices. So that was my main message. And while I was preparing for this talk, I thought to myself, okay, I'm a security researcher. Why am I not just starting a project on my own? So I decided to do that. I asked some of my hacker friends if they wanted to join me and do this on their spare time. And I started it as a hobby project. So I didn't have any funding or sponsoring for my day job when I started it. I just asked a couple of friends, do you want to help me and see if we can get some result on hacking medical devices? And they agreed, which I'm really grateful for. And I searched on eBay to see if I can find some devices to start hacking. And I was lucky, I found a pacemaker programmer that was the same brand as my own model. It was for sale for $500 on eBay. So I bought that with my own money, and also I found a lot of the home monitoring units that I'll get back to. But initially, when I woke up, or when I had the implant, and I was a security researcher, of course I wanted to know more as a researcher about how my own device works. So I started to search for information, and this was like 5 years ago. And I Googled the make and model of my pacemaker. I found a technical manual online, and I was really surprised when I started reading it, because I discovered that my device has 2 wireless communication interfaces. One of them is essentially connecting me to the internet, so that I'm a human part of the Internet of Things by having this implant. And no one informed me about this or asked for my consent to have this technology inside of my body. So I made this network diagram based on the information I found initially about my own device. So as you can see here, there's one wireless inductive near-field communication interface that is between the pacemaker and the programmer. I'm really happy that we have wireless communication between the device and the programmer, because surely I wouldn't want to be opened up and have a procedure or surgery every time you need to change the configuration settings. And I've been through a lot of tweaking and adjusting of the configuration settings. So that's really good that we have wireless communication. But it's very close distance communication. And I'm also in a hospital environment when this is switched on. So it's a very funny feeling when you're laying down, someone puts the reader head on top of your body and then initiates the communication with the device. And there is this touch screen on the programmer where the pacemaker technician or the doctor, just with a touch of a pen on this touch screen, he can make my heart go faster, slower, or switch it off. And that's actually what they do during the checkups. They run a test suite where you lay there and suddenly your heart starts beating faster, and then it starts beating slower, and then they usually warn you and say, no, we're going to test to see if you have a backup pulse. And then they switch it off. And then you feel like you're passing out in case you don't have a backup pulse that day. And I experienced that a couple of times. It's really scary. So I'm happy that I'm in a room at the hospital when this communication is taking place that can change settings of my device and affect my heart. And then we have the other wireless communication interface that I didn't know that my device had, because in my case, it's not switched on. But you can switch it on very easily just by touching the screen of the programmer or sending it a command. And this is a wireless communication interface that it reaches several meters. So it works the way that you have the home monitoring unit in your house, typically in your bedroom, and then will connect wirelessly to your device while you're sleeping at a distance of several meters. And the purpose of this is to collect log information from the device and then send this over the internet, over the telephone line, over the mobile telephone line, and then further on to a server which is at the vendors. It's not in my home country, Norway, it's abroad. And my patient data would be stored there, and there's a web portal where the healthcare professionals can log in and retrieve the information. This is very beneficial for a lot of patients because you can get a closer follow-up. You don't have to get in that often to the hospital or to your doctor's office. It's cost-saving because it saves trips to the hospital for the patient. And of course, it's the future with all this connectivity. We expect this. And some patients are even eager to get more connectivity or more data collected and also visible to them from their device. Because the way it works today is that this data is only visible to the healthcare professionals. It's not actually anything that's displayed on the smartphone of the user. So there are some ways to implement this where you're actually using a reader that you put on top of your chest, and then there's a Bluetooth connection to your phone, your smartphone, and then the data will be sent via your smartphone. But what is displayed on the smartphone to the user is only how long you should keep the device on top of your chest and when to remove it. There's no information about your own status and your own information. But as a security researcher, I'm kind of skeptical to this home monitoring. I have it switched on, and I would rather prefer to have a device without this connectivity. Because with connectivity comes vulnerability, and there's an increase in attack surface. And I know that a lot of this technology is implemented and maybe 10, 15 years ago, and it was a very different threat environment at that time. And cybersecurity and hacking was not part of the threat model, the risk model of the manufacturers when they initially designed this system. So there are some potential threats, things that can go wrong here. The device itself can be vulnerable. The access point or the home monitoring unit can be vulnerable. Also, your patient data is traveling across the internet. You have to trust the network operators. The mobile network can be compromised. The server where the data is collected can also be compromised. And what about the website where the doctor log in? So this creates a much broader area of attack and things that can go wrong. So what could possibly go wrong? Of course, you have to worry about patient privacy issues. And that's also where the regulators have mostly focused. Like in US, you have the HIPAA. In Europe, we have very strict data protection regulations. So this has been on the radar of the manufacturers. Other types of attacks are quite new and something that maybe no one thought about until a couple of years, or the last year or something. And one of them is the battery extortion attack, which is for us security professionals. You can compare it to a DOS, denial of service attack. So the device doesn't use a lot of, you need to be very cautious to not use up the battery of the device. And the pacing function is not really draining the battery that much. It's a very small electrical signal. But the wireless communication, it uses much more processing power. So you could essentially, by initiating a lot of communication to the device, you can drain the battery of the device prematurely. And also, since it's possible to program the device wirelessly, even though it's supposed to be a one-way direction of the home monitoring unit where log information is only retrieved from the device. It's not supposed to be used for programming the device. You can imagine scenarios where someone could try to inject fake messages or replay messages and maliciously use also the longer range wireless communication channel to change device settings, which could be potentially harming the patient. Like in my case, if someone switches off the functionality of pacing, that would really be really bad for me. And then we have more bad scenarios like death threats and extortion, which has become a bit of a problem the last year with the ransomware against hospitals, and now lately in the WannaCry, where we also saw ransomware on medical devices. But until now, of course, no ransomware has been found on medical implants. And the medical implants are not connected to the hospital network as other devices with the legacy operating systems. But it's possible to upload patches from the programmers to the devices, and the programmers can be a possible entrance point also to access medical devices. And then we have the, let's say, scenarios that I think you've seen on TV shows and that we also, that maybe is a bit more far-fetched. I don't see myself as that high-profile target that I should worry about remote assassination and cyber terrorism. But as it's been mentioned, Dick Cheney, he gave an interview where he disclosed that he had had the wireless communication interface of his cardiac implant removed because of these types of threats. And these threats have also become reality in a way that vulnerabilities have been disclosed the last year. We already discussed this before. I'm not going to go into the details. I just want to comment on this from a patient perspective. So the MedSec group, they disclosed vulnerabilities in centured medical implants, and the battery draining scenario was part of the vulnerabilities, and another one was the man-in-the-middle possibility to all online home monitoring units, which was really bad scenarios, because you could think about potentially misusing this in a way that you upload malicious code to many home monitoring units at the same time, which could affect a lot of patients. Patients were really left in fear, uncertainty, and doubt when this happened in August last year. If you read the Muddy Waters report, you would see that there was a cardiologist, a doctor, that gave advice to patients about switching off their home monitoring units. That was, what, you want to comment now? That was one thing that was actually in the report. So if patients read this report, probably not a lot of patients read that report, but a lot of patients saw the headlines, and that's where they get their information from. So it's, I don't have a century medical implant myself, but I could really feel it on my body. I could feel like empathy for all other patients that had this implant, and how confused they must have felt when they saw this advice and these types of headlines. And there was no official advisory from the manufacturer or from the FDA. It took, I think, 5 months until we got that information in January this year. And also, at the same time, there were recalls of the same types of devices, ICDs that had that battery depletion error, some lithium breaches that could cause the device to run out of battery within 24, 48 hours. And at least 2 patients were confirmed dead because of this failure. They didn't reach the hospital in time, they didn't get a replacement of their device, and they were dependent, and they died because the battery ran out prematurely. And the strong advice in that other case, which was disclosed in October last year, was that you should have the home monitoring unit on at all time, because that would give you a warning message and maybe save your life in case your battery ran out prematurely. So imagine being a patient getting all this conflicting advice, and at least if you're trying to make an informed decision, a risk-based decision on what to do, you would be really confused. And a lot of the doctors and healthcare providers were also confused and couldn't really give a good advice to their patients. It must have been really, felt really awful. So patients were waiting to get a surgery to have their device removed because of potential battery depletion. And at the same time, there were headlines about hacking threats against their devices. So why have we come up in this mess? Why are we in a situation where patients all around the world with implants cannot trust the technology inside of their body, like myself? We've already been through a lot of this in this summit, so I'm not going to go into all the details, but we struggle with legacy technology. That's a fact. So we need to figure out how to replace old technology, how to update system, how to have good procedures for giving security updates to devices and implants. This is something I've been thinking about. What would the perfect scenario be for me in case I find vulnerabilities in my own device? And after a while, a patch is released. How would I want to receive that patch to my device? The way it works today, and I only discovered this after actually doing some of the hacking and reverse engineering, I could see inside of the programmer in the file system there were firmware blobs that were sorted based on different pacemaker models. And this is the way that you actually can patch a pacemaker by giving the patch to the patient through the programmer in the hospital. We're talking about remote over-the-air updates in the car industry. I don't know if this is something that's viable for medical implants. I surely wouldn't want to receive a remote over-the-air update over the wireless network while I'm in a hotel abroad at a conference, for instance. I'd rather be in a room at a hospital with doctors around in case something goes wrong. And in case something goes wrong, who is liable? It's not as when we update our laptops. You have to sign this end-user license agreement and click yes. I accept the risks of installing this program on my computer. This is something that's it's not transparent at all how this works today. There's no available public information of how these software updates actually take place. And there is a lack of security testing and monitoring of security threats. It's insufficient reporting of incidents that might be related to cybersecurity. We don't have any confirmed adverse events because of hacking so far. But we don't know for sure. We don't know if something has gone unreported.